we want to go into greater depth into these important notes for a power series. In particular, let's start with number 3. So power series can be used to represent familiar functions, such as the transcendental functions of the trigonometric function, the exponential function, logarithmic functions, and others, but those 3 are very common. And those familiar functions can be represented in a completely different and new way, a way that's outside of what you're used to which you should say, really? And I say, yes, really, really, really. So let me show you this example right here. So I apologize. This is the 4th time I've made this video. So I've written on these papers before. My computer keeps eating it. So with any luck, I won't need number 5. All right. So this power series right here is a wholly different way to represent a function. And I think it's more powerful if you see it in Desmos, which is where I built this function. So here you can see in Desmos, and I have the power series. It's right here. I'm using n instead of k, which is what's written on the paper, but the theory still holds. So this is a function that you're building from the power series, but you'll notice I'm actually cutting it off. I don't go to infinity because of course Desmos can't handle infinity. So what I'm telling it, well, I guess it could, but I'm not going to make it. So I'm telling it to stop at letter I, and I'm going to let I vary. So if I let I be a small number, you can see, not 0, that would never work, curve, right? See how that curve is working? And as I let I get larger, you can see that the curve extends and expands out. And it's not easy for Desmos. Desmos is having to do some thinking as it goes. But you can see that this curve is getting closer and closer and closer to -2 to 2. Now at -2 and 2 itself, it's doing something kind of crazy. So we don't know what's going on there. But we can see that we have this smooth curve in the middle. And the section that is in the middle is leading to that idea of interval of convergence and radius of convergence and so on. And you can see from it appears -2 to 2, not including those values, that we actually have a interval of convergence. And the center of that interval is right there at 0. That's what I mean when I say, back on that previous note, you can have an interval converge sometimes. So for example, our particular curve is converging from -2 to 2, but then it diverges outside of that interval, right? That's possible. And that's what we're seeing in our graph. And that curve is creating a new curve, perhaps one that we've never seen before or never known before. Who knows, right? It's making a new function. All right, so that's what I mean by note 3. Note 4 is a bit more complicated. So note 4 is saying that the power series, and this is where power series really get used in practice, they're used to approximate algebraic, trigonometric, exponential, and logarithmic functions. Those are the most common. That cannot be evaluated exactly using arithmetic. So there is no way to find the exact value of an exponential function of, e to the 0.23. Right? It doesn't exist. So how do calculators approximate it all the time? Well, one of the things they do is use power series, believe it or not. A power series can be used to approximate messy functions, ugly algebraic functions that you can't really do the algebra for, but you can come up with a decimal approximation for. And so what we do is we're taking the continuous curve, which is e to the x. That's an exponential function. And I actually have 2, I'm calling them power series here. They're actually like power polynomials, sort of, because I'm letting this be a 1-term polynomial or power series, and this is a 3-term power series. Now let me explain what that means really quickly by showing you the Desmos graph of what I'm doing. Okay, so I have this curve, which is orange or yellow, which is e to the x. And I currently have this power series approximating it. Well, it's not really, well, you'll see. It's a power series, but it's a power series that stops at k = 1, which makes it something called a polynomial, a power polynomial. So I have this new polynomial approximating that curve. Of course, the yellow curve is not a polynomial curve, right? So a polynomial approximation will only be good for a little while, and then after a while it'll stray. In this particular case, it's only good very close to x = 0, right? When x = 0, y is equal to 1, and right around there the two are kind of lining up. Now they're not perfect. The blue line is not obviously exactly where the yellow curve is, but they're close, right? So then if I take k and I let there be more terms in this polynomial, then what's happening is, look, here I'll go to 3 because that's the other picture you have. Now the curve, look at how the curve is on top of that yellow e to the x curve. That new polynomial curve is on top of it, so it would make a good approximation for it, all the way from, say, like this dot over here of negative 0.5 to, well, definitely this dot over here of positive 0.5. So we've expanded the region for which that polynomial, which is the blue curve, would do a good job of approximating that yellow curve, right? That transcendental function that's ugly, right, and not easy to do in algebra. And of course, if I let k increase, you can see it wiggling along there, I think especially down at the bottom. So if you watch in the bottom left corner, you can see that curve is getting closer and closer, and it's expanding out. Eventually, the yellow curve will take off, and the blue curve doesn't do a good job. But it takes a while, right? On the left side, it happens pretty quick, but on the right side, it's going to happen much, much later. There you can start to see just a little bit of separation between the yellow and blue over there, right? That's because the polynomial is doing a good job of matching that exponential for a good long ways. So when it's saying, if we look back at the notes, it's saying that we can use that power series to approximate ugly functions that we don't particularly like dealing with. And that ugly function is a continuous curve, and I'm building a polynomial on top of it by building discrete packets. So I'm making a new kind of an nth term power series. We also call these polynomials, right? It's a new polynomial, p of x. And it's made out of discrete packets, right? So you're summing a discrete amount, and that does a good job of approximating that function. And the larger the n is, the larger I let that, the more terms there are in my polynomial, the better job it's going to do for approximating that continuous function, right? So I have a polynomial built from series. So I build a polynomial p of x from my series, right? So I take my series and, well, we'll see how it gets built, but it'll be ck, which is some coefficient, ck x to the k, something like that, right? So it'll have some polynomial that's built from this series, this power series, and we'll restrict it, and there it will do a better and better and better job as I let n increase, because I start at k equals 0 and I'm going to go to n. So as I let n increase from 1 to 3 to 7, that power series does a better and better job of approximating that function, but again, only for a particular window.